Hey guys, and welcome back to another video. In this video, we are talking about 3.1 related rates. Alright, so let's get started. Alright, so to begin with, let's start with the following problem. So we have a stone is dropped into a still pond, causing circular ripples to expand outward. The radius of the outer ripple is increasing at a constant rate of 3 centimeters per second. Find the rate at which the total area of the disturbed water is increasing at the instant the radius is 10 centimeters. Okay, so basically, the first step in all of these related rate types of problems is to just draw a picture. Okay, so we can imagine we can draw a picture of a bunch of ripples, like so. Okay, and it's saying that the outer ripple is increasing at a constant rate of 3 centimeters per second. So that means that this outer ripple right here, this is increasing at 3 centimeters per second. Okay? So we wish to find the rate at which the total area, so this total area is increasing. So basically, we want to find dA dt, right? The rate of change of area with respect to time. So how do we do this? Well, first we have to find an equation that relates what we want to what we know. So what do we know? Well, we know that the radius of the outer ripple is increasing at a constant rate of 3 centimeters per second. So we know that dr dt, right, that's equal to 3 centimeters per second. Do we know anything else? We also know that the instant that we want is when the radius is equal to 10 centimeters. So we know that we want r to be 10 centimeters. That's when we're interested. Okay, so so in this case, it's pretty easy, right? We simply need to apply the area of a circle. So the area of a circle is area equals pi times r squared. Okay, so then now we can differentiate both sides with respect to time. So I'll do that now. So differentiating both sides with respect to time. So let's see, what do we get? So the derivative of area with respect to time, that's simply just dA dt, and that's exactly what we want, right? And so then on the right hand side, we have pi r squared. So its derivative with respect to time. So first, remember, you have to use the chain rule. So first you have to differentiate with respect to r. So the derivative of this with respect to r is simply 2 pi r, and then we multiply by the derivative of the rate r with respect to time, so times a dr dt. Okay, and so now we can plug in everything that we know. So dA dt, that's what we're trying to solve for, so leave that alone for now, is equal to 2 pi, and then r we know is 10 centimeters, and then times dr dt, which we know is 3 centimeters per second. Okay, so then we can just evaluate all of this, and we get that dA dt is equal to 60 pi centimeters squared per second. All right, good. So notice how the first step was we drew a picture, right? So that's always helpful. And then we listed what we want and what we know. So then that way we can um, write our equation right here, okay? And then finally we substituted in right here, or first we differentiated and then we substituted in and then we solved. All right, good. All right, so let's do another problem. So this one is slightly more challenging. All right, so here, let's see, what does it say? It says, water is leaking out of an inverted conical tank at a rate of 2 cubic feet per minute. The tank has a top radius of 5 feet and a total height of 15 feet. At what rate is the water level decreasing when the water is exactly 6 feet deep? Okay, so basically we have um, a conical tank, so something like this, I'm gonna draw that a little bit better. Right? And we have that so the top radius, so this radius right here is 5 feet, okay? And then we're given that the total height is 15 feet. All right, good. And so we want to know the rate at which the water level is decreasing when the water is exactly 6 feet deep. So let's say the water level is this deep, right? So we'll let h represent the height of the water, and then the radius of the water level, we'll call that to be r. All right, good. So let's see, what do we know already? Well, we know that the water is leaking out at a rate of 2 cubic feet per minute, right? So we have 2 feet cubed per minute. So what could this possibly represent? Well, notice that we have feet cubed in the top, so that's like volume, and then over minutes, which is time. So you have volume over time. So basically, 2 feet per minute is equal to dV dt. All right, good. So we know that dV dt is equal to 2 feet cubed per minute. And we know that we want to, so, and then, okay, so now what do we want? Well, we want the rate at which the water level is decreasing. So we want dH dt, right? So, because h represents the height of the water, and so we want to know the rate of change of h. So dH dt, when, well, we want it when h is equal to 6, when it's 6 feet deep, right? Good. So now, based on this information, we can write an equation to relate all the variables together. So what equation should we use? Well, we can use the volume of a cone. So the volume of a cone is V equals 1/3 pi r squared h. All right. So now we have to be very careful though, because, okay, let's say we just differentiated right away from this equation. So we get that dV dt is equal to, let's see, we have 1/3 pi, and then we have 2rh dr dt plus r squared dH dt. So this would be what happened if we differentiated right away. And notice that we have more unknowns than what we know. So we know dV dt, right? We know that. Do we know the radius at this instant? No, we don't, right? So we don't know what the radius is. We know what the height is. We know the rate of change, or do we know the rate of change of the radius at this instant? We also don't know that. Again, we don't know the radius, and but we do know dH, and dH dt is what we're solving for. And technically, you could solve for the radius using like use like using similarities, but you still don't know what dr dt is. So basically, if you differentiate it right away, you have too many unknowns. So we're not going to do this, right? This is not good. So instead, what we're going to do is we're going to try to express the radius as a function of the height, right? We're going to try to express r as a function of h. So that way, we can get rid of the information that we don't know. So how do we do that? Well, we note that we have, essentially, we have two triangles that are similar to each other, right? So we have this bigger triangle up here. So we have this bigger triangle where the radius of this top part is 5, and then this height is 15, and then inside we have a smaller triangle where the radius of this is r and then the height is h. So notice that these two triangles are similar. So therefore we can use similarity to relate r and h together. So from the big triangle we have 5 over 15, and that should be equal to r over h in the smaller triangle. So then solving for r, we get that r is equal to 1/3 h, right? So now we're going to substitute this back into here, and let's see what do we get. So we get v is equal to 1/3 pi, r is 1/3 h, and then we have that squared times h. So let's simplify this a little bit. So we have 1/3 times 1/9, so that's 1/27 pi, and then we have h cubed. All right, good. So now notice that our lives are going to get so much easier if you differentiate this rather than if you differentiated this up here. All right. So let's differentiate both sides now with respect to time. Okay. So on the left-hand side, we simply have dv dt. And then on the right-hand side, well, we can pull the pi over 27 out because it's just a constant, right? And so now we have the derivative with respect to time of h cubed. Well, remember, we just differentiate first with respect to h. So with respect to h, it's just 3h squared, right, by the power rule. And then we multiply by the derivative of h with respect to t. So times dh dt. All right, good. So now let's plug in everything that we know. Do we know dv dt? Yes, we do. See, up here it says we know that dv dt is 2 feet cubed per minute. So we can plug that in. Okay, that's equal to pi over 27 times 3 3h squared. So do we know what h is? Well, yes, we know that we want dh dt when h is equal to 6 feet. So we could plug in 6 for h. So 3 times 6 feet squared, and then times dh dt. That's what we're trying to solve for. So we'll just leave that alone. Okay, good. So now let's try solving for dh dt. So you get that dh dt is equal to, so if you just put this into a calculator real quick, you will get that dh dt is equal to 0.159, and then units are just feet per minute. So that is the rate of change of the height when the height of the water is 6 feet. Okay, good. So now let's move on to the next problem. All right. A spotlight is placed on the ground 20 feet away from a vertical wall. A man 6 feet tall starts at the spotlight and walks directly toward the wall at a constant rate of 4 feet per second. How fast is the length of his shadow on the wall changing at the instant he is 8 feet away from the wall? Alright, so remember, first step is we must draw a picture. So we have some vertical wall. So I'll draw that vertical wall right here. Right? Good. And then we have at 20 feet away, we have a spotlight. So let's say the spotlight is over here, right? And so 20 feet away, so this length is 20 feet. All right, good. So then we have a 6-foot tall man that starts at the spotlight and he's walking toward the wall. So I'll just draw a line segment to represent the man, and I'll say this is 6 feet in length, right? So this represents the man. And so we can draw this sort of triangle. All right, very good. So then basically this length right here, this length h, this represents the length of his shadow, right? So we want to know how fast is the length of the shadow on the wall changing. So basically we want dh dt. So now we have to be very careful. So it says, okay, so first we're given that he's walking toward the wall at a constant rate of 4 feet per second. So what does that mean? Well, if we let x be the distance from the man to the spotlight, okay, So it's basically saying, so this will be know. So basically it's saying that we know that the rate of change of x with respect to time is equal to 4 feet per second, right? That's what that means. So then when it says how fast is the length of a shadow on the wall changing at the instant he's 8 feet away from the wall. So 8 feet away from the wall. So remember, x is the distance the man is from the spotlight, but this is saying the distance he is from the wall. So it's basically when, like this length right here, when that's equal to 8 feet. Okay, so then if this length is equal to 8 feet, then what is x in that case? Well, we know that the total length of the bottom of the ground is 20 feet, and then we can subtract 8 feet, so we get that x is equal to 12 feet. So basically, we want dHdt when x is equal to 12. All right, so that's what we want. So then, now let's try constructing an equation to relate all of our variables together. So again, notice that we must use similar triangles, right? So we note that these triangles, oops, what happened? Okay, there we go, are similar because they both have right angles, and then they both share this common angle right there. So therefore, by angle similarity postulate, these two triangles are similar. So therefore, by similarity we know that h over 20 should be equal to 6 over x. All right. So then we can solve for h. So we get that h is equal to 120 over x. All right, good. So now we differentiate both sides with respect to time. So on the left-hand side, we simply get dh dt. And then on the right-hand side, we get negative 120 over x squared times dx dt. And this is just like parallel, right? Because like you can rewrite this as 120x to the negative 1. So then you get negative 120x to the negative 2. So that's just negative 120 over x squared. All right, good. So now, next step, we've differentiated. So now we must plug in everything that we know. So dHdt is what we're solving for. So this is equal to negative 120 over x squared. So we want dHdt when x is equal to 12. So we're going to plug in 12 for x, and we have that squared, and then times dx dt. Well, we know that dx dt up here, we're given that it's 4 feet per second. Okay, so plug that in, 4. All right, so now we can evaluate dH dt, and if you plug this into a calculator or something, you should get that dH dt is equal to 10 over 3 feet per second, which is approximately 3.333 feet per second. All right, nice. Okay, so yeah, just to recap, the general approach in these related rate problem is first you want to draw a picture, right? So that helps you see, like, picture what's going on. And then from that picture and from the word problem itself, you can write down what you know and what you want, right? So just write down what you already know and then what you want, what you're trying to solve for. And then after that, you can write an equation. Okay, so if we have, this is step 1, so this is step 2, writing what you know and want. And then step 3, writing an equation to relate all the variables together. And then sometimes you have an intermediate step 4, which is like trying to get rid of some of the variables so that you know, like as we saw in the previous example where you wrote r as a function of h. So that'd be like the intermediate step 4. So just like, I'll just say like rewriting variables. All right. And then finally, we have step 5, which is differentiating, right? And then step 6 is just plugging in and solve. All right. So it's like 5 to 6 steps to solve these types of problems. All right. So that wraps up this video on related rates. I hope you enjoyed and found this video helpful. And if you did, please make sure to leave a like and don't forget to subscribe. I'll see you guys in the next video.